Now section 19.1 on page 281 deals with real questions, so let's just do it right now. Question 3 says this: I've got vector AB represented like that, is defined as column vector 2 across and 1 down, hence 2 minus 1 as a column vector. And it says that question 3, which of these column vectors are parallel to AB? Well, I'm given this one as a scenario. So I've got 4 and minus 2. Now I can see straight away that links directly to vector AB. If I pull out a common factor of 2 and get a scalar of 2, then I go 2 lots of minus 1, so 2 2's make 4, 2 lots of minus 1 makes minus 2, and of course look, the 2 minus 1 and 2 minus 1 are the same. Therefore 4 minus 2 is parallel to 2 minus 1, and of course 2 is the scalar or multiplier or multiple, and that's good. I mean, I can prove it by a little picky if you want me to. Look, so 2 minus 1 looks like this, 2 across 1 down. I've got to put an arrow on it, otherwise it's naughty, and that's root journey A to B. And here I've got 2 lots of 2 minus 1, which is 4 minus 2. So let me just draw it for you. 4 across 2 down, there it is. They even look parallel, don't they? So that is 4 minus 2. I could of course proved it better by going 2 across and 1 down. There's 2 minus 1. Then carrying on where I left off, 2 across and 1 down, and look, I end up exactly the same thing as 4 minus 2. So this definitely works. So they're equal, and that's great. So basically I've shown by little pictures and little vector diagrams that 4 minus 2 runs very parallel, totally parallel to 2 minus 1. What about the next one? Well, I can tell you the next one is a complete waste of time. The reason being is because I cannot pull out a common factor of 3 and 0 to end up with 2 minus 1. So it can't be done. Next one. Looks a bit tricky. Minus 4 and 2. Well, look at it. If these are all positive numbers, then 4 and 2, well, 4 is twice as big as 2, and 2 is twice as big as 1. So I think a 2 is involved somehow in a scalar of vector 2 minus 1. So if I put 2 and 1 there, it's a good start. Now 2 times 2 makes 4, but I want minus 4, so I've got to put a negative in front of the 2. So minus 2 times 2 makes minus 4, that's correct, and minus 2 times minus 1 makes plus 2. And look, minus 1 matches the minus 1 in vector AB, and the 2 matches the 2, the top part or the horizontal movement of vector AB. So therefore that's completely correct. That's the phone, and I have to ignore it. So yeah, therefore parallel. Alright, so how would I prove that to you? By using a picture. Well, let's try and do it, shall we? Let me just draw the original. So the original is going to be 2 minus 1. That's that one, and that's vector AB. And now I've got to go to, minus 4, 2. Just draw that one for you. So start here. I don't know. Minus 4. Start here. 1, 2, 3, 4, and 2 up. Look, there it is. Totally parallel to that one. But this time I'm going that way, up the hill. 4 to the left, 2 up. Now remember, when you prove that they're parallel, you've got to take out a common factor or multiplier or scalar. Take a common factor out of these two numbers, I mean, and then end up with a multiple outside the bracket, so to speak. So that's what we've got. Now look, please note, you can be parallel but running opposite directions. It's not about getting the parallelness correct. You can in fact ignore the direction. You can be parallel but running opposite directions. Alright, so this is just about proving that they're parallel, and the picture proves it as well. Let's do the next one. I've got to do minus 10 and 5. Well, my gut feeling is of course it's parallel, because 2 5s make 10 and 5 1s make 5, so I reckon I've got something going there. We'll worry about the signs in a minute. Now I've got to get from 2 down to minus 10, which means I've got to multiply by minus 5. And how do I get from minus 5 times 1 to 5? Well, the 1's got to be negative as well. Well, it's got to be, because if it wasn't negative, it would not run parallel to vector AB, would it? Let's just test again. 2 minus 1 is the original vector AB, so that's AB. And minus 5 times vector AB? Well, minus 5 times 2 is minus 10. Yep. Minus 5 times minus 1 is plus 5. Yep. So it's totally correct. Therefore, parallel. If you want me to draw it, let me just try and do it so you can get a visual picture on that. Right, let's start with original vector 2 minus 1. So 2 across, oops, not very good. Start there. 2 across, 1 down. That's in that direction. And I've got to do minus 10, 5. Let's hope it fits. Let's try and go over here then, shall we? Minus 10, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Oh, I've crashed into that. Never mind. I've done it though, and I don't know, from where I'm sitting, that looks pretty parallel. This is a 5 times longer road than this little road, and it's running the opposite direction. So they're definitely parallel. And the last one is 5, 4. Here it is, 5, 4. Why has it gone black? Anyway, no, I can't convert a 5, 4 into a 2, 1, whatever I do, or 2 minus 1. There's no common factor of 5 and 4, which will leave me with 2 and minus 1 inside. So, no, not parallel, that one. And part B says, for those vectors which are parallel, write down as a multiple of AB. Well, I've done it, haven't I? So, for example, 4 minus 2 is basically 2 lots of 2 minus 1. That's a multiple. Minus 4, 2 becomes minus 2 lots of 2 minus 1. That's a multiple. And this one here, minus 5, minus 10, 5 becomes minus 5 lots of 2 minus 1. That's a multiple, so I've done it really. Question 4. I think I'll do question 4. I don't want to make the video too long though. I'm being given this in question 4. I've got vector AB. It goes like that. It's defined as 3 across and 2 up. And BC is defined as 1 across and 4 down. It's minus 4. So I've got this as information. I've got to draw diagrams showing AB and BC. Oh, okay. Well, AB is basically 3 across. Let's start with that. 3 across and 2 up. And let's label it AB because I've got to do that. A to B. And then it says BC. Well, that's 1 minus 4. So let's just start over here. We can go 1 across and 4 down. 1, 2, 3, 4. And that's BC. Going in the direction shown by the arrow. It's important to put an arrow. And then it says write AC as a column vector. Right. Very easy. I've got AB going that way. If I add on BC, I will end up with AC. And if you like, in one way of thinking about it is to imagine these B's cancelling out. But we'll see it as a picture why that's in fact true. So AC is a column vector. So let's add them, shall we? Right, I've got 3, 2. So I'm going 3 across and 2 up. And I'm adding on a journey 1 across to the right and 4 down. Let's see where we end up. Well, 3 plus 1, the net effect is 4 across to the right. And 2 plus minus 4 is the net effect of 2 down, or minus 2. So let me try and draw that as a picture to see if it actually does hold together as true. Let's go a little bit slimmer on that. We'll work in red. Right, 3, 2. Does it work? Start here. 1, 2, 3, 2. So that part is my AB part of the journey. Alright, in that direction. Then I want to go 1 minus 4. So this is B to C now. 1 minus 4. 1, 2, 3, 4. Stop there. And this is my C part, and this is the arrow from B to C. Now if I've got this right, then the vector 4 minus 2 should join A to C. Well, let's just try it, shall we? 4 minus 2. 1, 2, 3, 4. Minus 1, minus 2. I'm bang on. And it therefore works perfectly, doesn't it? So there it is. So BC is like going AB followed by a BC, which is like going from A to C direct. So in a way, you've cancelled out the town B. You've gone straight from town A to town C. You've not gone from town A to town B, had a little break, then go from town B to town C. You've gone directly through. So in a way, in your thinking, you can say, well, let's cancel out the middleman, go straight from A to C, add up the two vectors and go direct. And that's the first vector diagram you come across at grade A. Question 5 looks terrible. I'll do a bit of it. As much as I've got time for, I'll do. Which of these statements are true and which are false, and give a reason? This is question 5. Hope the video isn't too long. I've got 2x and minus 4y as a column vector. Don't worry about x and y. In fact, it's helpful. X is like going across and y is like up and down, isn't it? Is it in the same direction as 5x followed by minus 10y? Right. Are they in the same direction? Are they parallel? Yes, I can take out a common factor. If you look very carefully, if I take out 2.5, if you look at, for example, from 2 to 5, I multiply by 2.5. From 4 to 10, or minus 4 to minus 10, I'm multiplying by 2.5. Therefore, 5x over minus 10y is like saying 2.5 times 2x and minus 4y. Okay, 2.5 times 2x, 5x, sorted. 2.5 times minus 4 is minus 10. So therefore, they are parallel. A bit more tricky than just playing with numbers, isn't it? Playing with x's and y's as well. Let's try the other one. Are these parallel? Oh, sorry, do they run in opposite directions? Let's just take a look. So if they're running opposite directions, they've got to be parallel. Yes, that's the bare minimum requirement. And the arrows will be, and the signs will be flipped as well. Let's just look at it. I've got 1.2x and 0.2x and 1.2y's. I've got that, and I'm being parallel but opposite to minus x and minus 6y. Well, ignore the signs for the moment. I can see that if I multiply 0.2 times 5, I will get 1. If I multiply 1.2 by 5, because 12 5s are 60, 1.2 times 5 will be 6. So I know for sure they're parallel. Now, if I can take out a common factor to get from x and 6y down to 0.2x and 1.2y, then I've proved it all the more. So let me have a look. Minus x and minus 6y. I'm going to take out 5 lots. I think it's going to be minus 5 lots. So minus 0.5 times 0.2 will give me minus 1. That's perfectly correct. And minus 5 times 1.2 will give me minus 6. It's perfectly correct. Sorry, minus 1.2, because 5 12s are 60. Sorry, my confusion here. Let's rub it out, make it pretty. So that's going to be 1.2y. Alright, so yeah, that is the same as that. They're equal to each other, but it's minus 5 times as big. So it's therefore poking round the other way. So it's a bit difficult to draw 0.1s and 1.2s, so I'm not going to try that. But please note I have a common vector running in the same direction, but by multiplying this vector, the common vector, by minus 5, I'm going to flip it going in the other direction because it's negative, and it will be 5 times the magnitude of the original. So yeah, it's true, these are parallel and run in opposite directions. Spell it fully, directions. And there is the last one, parallel and running in the same direction. Well, I'll draw it for you anyway and give you an answer straight away, and the answer is no. So I'm comparing that with minus 15x, minus 15y, and I've got 25x's. Well, absolutely no chance. Well, let's just look at that, shall we? Minus 5 and 3. Well, it mustn't be conned by the signs. Now look, x and y are not related together, so I can see multiplying minus 15 by 3 gives me minus 15, but 3 times 3 doesn't make 25, so this doesn't work. So are they true? Parallel and run in the same direction? Not parallel. Do they run in the same direction? They can't, because the vectors are different. Even if we were to just ignore the x and the y straight away, the numbers don't match. For example, 3 5s would make 15, 3 3s would make 25. So you won't get them to be to run in the same direction at all. So they're not parallel and do not run in the same direction. Now I'm feeling this video's gone a little bit long, so I'm going to have to stop there and maybe do one or two other questions on top of that.